So, welcome to Chemical Principles 2 course. So, this is the course that is typically taught in the second semester of first year students in IIT Pune, and in this particular course we study the subject of thermodynamics. So, why it is called Chemical Principles 2 is that in the first semester we have Chemical Principles 1 where we study structure of atoms, which typically gives us an idea about how to estimate the energy of the particular matter, or how the matter is constituted of. For example, we know the hydrogen atom is constituted of proton and electron, and the behavior of the electron gives rise to all the orbitals and things like that. And then in the second semester we study Chemical Principles 2 where we see how matter changes from one form to the other form. So, and that, as you will as you see, that is governed by a different principle, and that principle will tell you for any process, any change that happens, how that change will go from one place to another place, how the change will actually take place. That is governed by this particular subject. So, that is why we call that Chemical Principles 2. Thermodynamics, we know that this particular course as thermodynamics is a subject to study the change of matter. So, as you will see that the thermodynamics is actually present everywhere. I will give you some examples here. So, let us say a process is going from A to B. We will define what is A and we will define what is B. Now, any change, anything that you can think of will have a governing principle of thermodynamics behind it. I will give you some examples. Change of matter, for example, chemical reactions, atoms going to molecules, change of matter. For example, you are breaking something, that will be a change of matter. Whether it is chemical reactions or not, if there is a change of matter, it has to be governed by thermodynamics. Then change of various forms of energy, for example, a change from solar energy to electrical energy to chemical and mechanical energy, etc., will be also governed by a thermodynamical principle. Change of phases, for example, water has, we know, 3 phases, right, ice, water and vapor phase. Again the changes will be governed by thermodynamic principle. Change of heat to work, which is most important, because as you will see that this change, particular change from heat to work, is one of the motivations for this thermodynamics to come about. A lot of people have tried before to make the heat into a work this thing, and then combination of all the above. So, if I have missed anything and if I have not stated anything here that talks about the change, that also will be governed by the principle of thermodynamics. Only thing that we have to understand that where and how these changes are taking place. Some of the examples will be given here. Now, all these changes, as you will see, that in rhyming with the Lord of the Ring, that there is only one rule that allows all those change. Have you read Lord of the Rings? If you have read, there was a ring to rule them all. Here there is a law that rules every changes that happen, and this particular course is all about understanding that rule. It is very simple rule, but if we understand that rule, we will actually have a grasp of all those thermodynamic processes. When you will look at them, let us say for example, when you came to this particular class from your home, then you must have noticed lot of changes, lot of things that were there before and not there today, or there in the morning and not now. All those changes, if you note it down, you may find an explanation for those changes when you study or learn this particular course. We will give some examples here. For let's say let's talk about photosynthesis. In photosynthesis, what happens, all of us know that the trees actually will take carbon dioxide and water, and with the help of sunlight it will produce glucose and oxygen, right. Now, interesting thing is that is a change of matter, because there is a chemical reaction is happening. Carbon dioxide is different matter, water is a different matter, and glucose is completely different matter, right. So, there is a change of matter going on. Again, this will be governed by thermodynamic principle, and interestingly you see that same glucose is actually used by animals to, and with the help of oxygen will produce carbon dioxide back and water almost like a cyclic process, right, and it will store the energy in ATP. So essentially what has happened that the sunlight, the solar energy has been converted to a chemical energy. Why do we call chemical energy will come, will come clear later on, that why do we call ATP as chemical energy, we will explain that later. But right now I take my word for it that the energy that was there in the sun now has been stored in the form of chemical energy. So this change from one form of energy to another form of energy, let us say if I forget about everything else, if I forget about the change of matter in these two steps, then the overall change from solar energy to chemical energy is also a process that is governed by thermodynamic principle. Now let us talk about molecule of life. Thermodynamics is everywhere. So let us talk about atoms. So we know that common atoms like carbon, nitrogen, phosphorus, sulfur, oxygen, they combine to form molecule, right. Those molecules combine to form supramolecules like DNA. Those supramolecules assemble together and form organelles. Those organelles are there present in cell. That cell gives tissue, then organs, organ system and human being. So ultimately we are all made of those atoms and molecules. When we say we, every atom in our body, every cell, if you break down the cell, then you will actually get the atom finally, right. So including the one that is there in our brain, including the one that is enabling us to talk right now, is made up of atoms finally, and that atoms will form or combine following the principle of thermodynamics. So in our body lot of reactions are going on right now, chemical reactions. When you talk about biology as a different subject, you will see that at the end all subjects actually will amalgamate together, right, because when you talk about a biology, we will talk about a biological system, but inside a biological system there will be chemical processes happening. Chemical processes will actually be governed by physical principles. Physical principles can be understood by mathematical equations to some extent. So let us say here, so this is a kinesin protein, and the job of this particular protein is to carry a big load, big nanometer scale, this load, and this is I think a cartoon work where this particular system is taking the ATP energy, using the energy stored in ATP and performing a mechanical work which is work. So work is a work, right, and that is being performed by this kinesin protein. So this again, as we said, that this will also be followed by thermodynamic principles. And let us talk about another thing. So when we open our eyes in the morning, thermodynamic principle starts happening. For example, when light falls into an object and then comes to our eye, something happens. What happens is that there is a chemical change that happens. So there is a all trans retinol molecule that photoisomerizes to cis retinol. So this isomerization can only happen because of the photon that falls in our eye, and this photon, we know that we cannot see all possible lights, right, we see only in the range of visible light, 400 nanometer to 800 nanometer, in that range. So that means a particular frequency of light has to, or particular frequency of light can activate this trans retinol and form cis retinol. So thermodynamics determine these changes. So if let us say less than 400 nanometer light falls, that is also an electromagnetic radiation, but somehow that cannot activate this chemical transformation, and because that cannot activate that chemical transformation, one cannot see. So that means even in our vision actually there are chemical changes happening, and in that chemical change thermodynamics is playing a very important role. So we have talked about that. So now different phases of molecule, we have seen that, we know the example of phases of water. Actually water has many more phases, but we will just talk about standard 3 phases that we know. One is ice, another is water, there is vapor, and they form a cycle. Now it turns out that one cannot just take a ice and make it water. it needs a particular condition. We all know that those conditions, and then vapor also requires certain conditions, certain temperature and pressure is required for one form of the matter to be stable, one phase of the matter to be stable, right. And let us talk about carbon. So, carbon has also different forms. One is like graphite, which we have in the pencil. Another is diamond, very different, right. Diamond is extremely costly. Imagine we could convert same carbon from graphite to diamond, how nice it would have been, right. But again, they form at certain conditions, and carbon soot, which actually nobody cares, just carbon dust, right. So, these all three forms unthinkably is actually allotropes of the same thing, carbon. So, here matter is not changing, but the phase of the matter, how they are arranged in that particular molecule is actually changing, and therefore, that physical properties, whether light will reflect from that or not, for example in diamond, will actually be different. So, that is a property of the matter, and that property of the matter is again another subject, but the point is that these formations will be governed by thermodynamic principle. And let us now talk about another very interesting subject is that thermodynamics actually even helped for the existence of this our physical universe itself. So, we know that our universe is 13.7 billion, approximately 13.7 billion years old, and it is believed that it started with a big bang, which was at which point the universe was of a point size, and then it expanded extremely quickly, within 10 to the power minus 36 second, expanded to a large form, and then it kept on expanding till this point that we are here. And then it is believed that the temperature was 10 to the power 31 Kelvin during that time, at the time of Big Bang. So, it was only energy and nothing else. Now, soon from that energy matter got created. So, hydrogen and helium were the first two elements that got created after the Big Bang. First of all, electron had to combine, and hydrogen had to form and all that, and then the expansion cooled down the overall temperature of the universe, and right now the temperature of the universe is around 2.7 Kelvin. So, that expansion process is related, you will see later on that it is somewhat related to an adiabatic expansion that we will come to know later on. Adiabatic expansion where your total energy is actually same. What is happening is that with that energy, when a system does work, then temperature reduces, because system is using its own energy to do the work. So, you can think of that this as similar to that, and lot of other matters that got created during the Big Bang, where explosion due to explosion of stars and many other things. So, our Earth got formed around, let us say 4.6 billion years ago approximately, and at that point we had all the matters present. So, energy conversion of energy to matter typically does not happen in normal environment, like the earthly environment, because in order to create any matter above this helium, you need sufficiently high amount of energy to convert that, which is not present, of course. So, right now people are trying to make matter in large hadron collider and all, and that too they exist only for a very brief moment. So, the fact that it got cooled down, and the fact that universe has expanded from a point to this 100 billion light years long universe, it has to do with the principle of thermodynamics also. We will come to that, come to know about that and appreciate this particular fact later on when we will know more about thermodynamics. So, but practically speaking, this particular subject came into existence because many scientists tried to make efficient engines around 17th to 19th century. So because of war, because of many other things, they try to make engines that will run with more efficiency. Like engines typically mean that we put some heat and then we'll get some power out of it. So thermodynamics is basically therm plus dynamics, dynamo, which is like heat and power. It's all about like how to convert heat to power, heat to work and things like that. So that's where the name thermodynamics actually came. And engines, as I said, engines is basically conversion of heat to work. So electrical engine will convert electrical energy to work, battery like chemical energy to work. Refrigerator actually will use electrical energy and do the work and cool the system. Refrigerator is typically the opposite one, where we do the work and get the heat out. So when you talk about engine, there can be two types of engine. One is like internal combustion engine, which is there in our cars, and another is external combustion engine, which is there in the like trains, steam engines. So the steam engine, you put coal, you burn the coal, and the heat will actually make the water to a vapor, steam, and the steam will put a pressure on the piston, and then piston will do the work, move. So this particular thing, that how much coal you need, how much heat you need in order to convert to work, essentially depends on your efficiency. So the origin of thermodynamics came primarily at that point in search of a better and better engine. Okay. And the efficiency of one particular engine, as you will see, that again is dictated by laws of thermodynamics. So then to summarize, if we say that thermodynamics is nothing but conversion of heat to work to energy, these three things. So it will just go from here to here to here and all other possible combinations. These three things, if you narrow it down to the smallest possible things, then you will see that this principle, what all it is doing is giving you a guidebook that how to convert heat to work, work to energy, energy to work, energy to heat. Heat and energy, we are keeping it separate right now for a reason. And as you will see that all these processes actually is governed by something called entropy. So this is like entropy, you can think of that as a gatekeeper. So when the gatekeeper will open the gate, anybody can go, right? So when the gatekeeper entropy will open the gate for heat to be converted to work, then only it will happen, otherwise it will not happen. Thermodynamics is a term which is coined by William Thomson in 1854. So he synthesized the subject of Carnot's motive power of heat and Joule's mechanical equivalent of heat and Clausius' mechanical theory of heat into a subject called thermodynamics. Right now we do not know about them, but we will come to know about that as we go along the subject. Okay. Another interesting thing that I would like to tell you about thermodynamics is that, as I said, that many people try to make better and better engines at that point around 18th and 19th century. So better means the most efficient engine is where you do not have to put any energy, you get the work out of it, right. It is called perpetual motion machine. So perpetual motion machine is something that things will automatically happen. So let us say perpetual motion machine is there, let us say there is a overbalanced wheel. So this wheel looks like that it will only rotate on this side and not on the other side. If you design something like that, imagine that if you can rotate the wheel in one direction, you can get work done out of it, and the way it is designed is supposed to move only in one direction, and therefore it will supposed to give you work out of that. Do you think it will work? So this is just one example. Several people have tried to make this kind of perpetual motion machine and asked for a patent. So US office stopped taking any patent at some point, any patent application at some point, which they said that you have to show a prototype of the particular perpetual motion machine, then only patent application will be accepted, because lot of people tried and lot of people, actually everybody failed to make perpetual motion machine. thermodynamics will tell you that it is impossible to make a machine that runs forever without any input. So if something happens without any input and runs forever, is called perpetual motion machine of first kind. But there is something called perpetual motion machine of second kind. So perpetual motion machine of first kind will violate first law of thermodynamics. So we will see that later on, first law. And perpetual machine of second kind will violate second law. So we don't know about first law and second law right now, but I can tell you in the first law is basically that without input energy things will work. That means people say that free lunch. So you are not paying for your lunch but still get lunch. So first law is equivalent to getting a free lunch, and you know there is no free lunch. There is a saying, right, there is no free lunch. You have to do work for whatever you are going to get. For example, you have to study for getting your marks, something like that. Perpetual motion machine of second kind says that you pay for it fine, but you cannot eat in full. You have to leave something for others. So I pay for 10 rupees, I can only eat up to 8 rupees. Like I have to leave out 2. So this particular machine, which is called ammonia motor, also called zero motor, by somebody called John Gamgee, he made that in 1890s, and he convinced US government that this will work. So the idea is that there is a ammonia here, liquid ammonia. So liquid ammonia is around minus 33 degrees centigrade, it is in liquid form, ammonia. And then if you put it in an enclosed environment, then of course this is ammonia vapor, this place, and outside there is like sunlight is there, so that is why it is vaporized, and it creates a 4 atmosphere pressure in this, which goes here and put pressure on the piston. And the idea is that when it put pressure on the piston, it will do the work. By doing the work, it will get cooled down, and again it will become liquid and will come in the chamber. That way continuously that liquid ammonia will do the work. So it will work, it will get cooled down because of the work, because it is using its energy, right, cool down, and then it will become liquid again and come to this one. So you see there is a source here. What is the source? Source is the sunlight, which is making it to vaporize, right, but there is no sink. So you will see later on that it is not working because it will not automatically get cooled down. You need a refrigerator to cool the ammonia back to liquid, because in order to cool down, the heat that is there in that vapor of ammonia has to go out, right. So that means now heat will go out from low temperature to high temperature. That is not possible in thermodynamics. That is violated by second law of thermodynamics without doing any work, by the way. It can go from low to high. Refrigerator is made for that, right. It goes out continuously from 4 degrees centigrade to our normal room temperature. That is how we keep things cool. Or let us say deep fridge where it is minus 20 degree. So because we do work there, but without doing any work, spontaneously heat cannot go from low temperature to high temperature. And John Gamgee did not think about that. Okay, that is very unfortunate. He had to suicide later on. So the thing is, but he convinced and he got a patent for this. I think this is the I'm not 100% sure, but this is the first and last patent that anybody got on perpetual motion machine. But it never worked. In fact, you will be convinced, knowing thermodynamics, that it is not possible to make a perpetual motion machine. So in this particular course, we are going to use some books that I am going to mention. So these are the one book is Physical Chemistry by Selby, Alberti and Bowendi, and another one by Atkins. These two typically will be required for classical thermodynamics part, and then we will also talk about molecular thermodynamics, where we will explain the principles of thermodynamics from atoms and molecules, and for that we will follow these two books by Hansen and Green and by Kendall, and we will mention as the time progresses that when and how these books will be required, And there is another book by Kellen that has a slightly different approach of postulate based thermodynamics. We will talk about that also later on when the time comes, but these 5 books, they are fantastic books, and if we can understand them, we will get a very good idea on and grasp on this particular subject of thermodynamics or chemical principles too. So now we are going to switch to demos. So here we are going to show you some simple demonstrations of conversion of different forms of energy. So although one thing is certainly sure is that these demos are there everywhere. It's not that you need really any particular demo to show here, but you can think of demonstrations of thermodynamics at every point. For example, when I rub my hand, heat gets generated, which is mechanical energy converting to heat. So at every point you can think of a change and associate a thermodynamics principle with that. But here what we are going to show a few of the demonstrations of how actual things will work, engines and different forms of energies are used for getting mechanical work. These are very simple tools for that. So Raymond, shall you come? Raymond is going to show you. We have different cool devices. They are extremely cheap. You can buy them online. It's like 400 rupees. Although if you buy separately, it will be even cheaper. What we are actually trying to do here, we are trying to use solar energy to convert to 3 different types of energy. One is mechanical energy, in which the fan will actually rotate. Another is light energy, the bulb will actually lit, and sound energy, where the buzzer will make sound. Okay. So solar energy gets converted into 3 different forms of energy. That's what we are going to show in the first demonstration. But note that we are not under the sun, but solar energy is nothing but photon. So if we have enough photon with enough photon intensity, it will work. So we will see whether things are working or not. So we will try the sound first. Sound will definitely work. Yeah. So we have connected one part, then we are going to connect another part, and okay. So we need stronger light. I'll try my mobile and see if it works. Slightly better. Okay. So now we are going to show you the light energy, which is also will not be that much of a problem. So you have connected one end, and we are going to connect the other end, and we will see 1, 2, 3. So this light probably you cannot see, right? We have to make it really dark to see the light. Can you see the red light? Okay. So now we have converted solar energy into 2 different forms. One is sound, another is light. And now we are going to do mechanical one, which is slightly difficult. Our experience says that mechanical one requires really strong sun. If you put it under the sun or 100-watt bulb, it will work. See, all depends on solar efficiency, right? It is only to show that it works. Let me just give it a nudge a little bit. No, this really requires more power. But we have seen that it works when you put it under the sun. Just can you focus on this? See, light and all smoothly happening. Mechanical work has frictions also, right? So you need more power. And depending on how much power it is using, these solar cells are they're combined together to make this particular solar plate. This is a solar plate. So it's like extremely cheap way of demonstrating that how one can convert one from another form. Now this one is an example of hydrothermal power. So basically we can use power of falling water. So we have in many places the waterfalls are there, right? So if we have the similar situation and if we do that, if we put water here, then what will happen is that this mechanical energy that is there will give us electricity. We have demonstrated that. As you can see, the flickering light. Now another demonstration is wind power. So in many places you will see that where there is a strong wind, that wind which is natural, right, we are always looking for renewable energies. What is renewable energy? Finally, renewable energy is that we do not want to use our chemical energy which is stored in coals and other things to produce energies. We can use natural energies which is sunlight, wind, waterfalls. They are already naturally present. So we can use their energy to get the energy needs. So this is another example where you can use wind to get the electrical energy. So now we cannot get wind here. So therefore prototype of wind is this particular thing. So you see this fan will rotate, charging that this particular motor, which is now getting converted to the electrical energy. So right now we are actually rotating the fan using the help of this particular pulley, but we can take it out. We can take it out and we can just blow this. See, it has to move by the force of wind, right? We can blow this. We have put it in front of a fan, and then we could make this light to glow. So these are like different forms of chemical changes that are happening that you can see here. So right now we have seen that conversion of solar energy to light energy, and mechanical energy, sound energy, and then hydrothermal energy. So water will convert to electricity, and this one. But also we can show you the changes from that is there in chemical energy that is stored, like for example ATP. We talked about ATP, right? That ATP has stored energy. So forget about ATP, we have stored energy in sodium chloride, right? We are going to demonstrate that energy that is stored in sodium chloride, how one can use it. So can you come and do that demonstration? So we are going to show you the effect of chemical energy converting to light energy, right? No, mechanical energy. We are converting chemical energy into mechanical energy. So he is going to demonstrate that. So you see that there are two electrodes here in the glass, and then it is connected to a fan. Okay, it's actually connected. It is not connected. Not connected. So he is going to connect to a fan. So right now this electrode is dipped in plain water. We are not getting any energy out of water. Okay. However, we are going to use some chemicals. We want to use the power of chemical into converting to mechanical energy. Again, that's a conversion, and that conversion will follow thermodynamics principle. So here this is as you can see, can zoom it in and say this is a glucose. So we are going to put glucose here. Do you expect anything to change? No. So let's put glucose and see what happens. You have to start it. Yeah, I think this is. So it's a plain glucose solution. See, remember this same glucose gives us energy, isn't it? So that glucose, when we eat, we get the energy stored in our ATP, but that glucose is not going to give us the mechanical energy here. That gives us mechanical energy in our body, where that kinesin proteins using ATP move something, right? But here it cannot do that. So fan is not working. However, we can use another chemical which is we eat every day, is called table salt, sodium chloride. We are going to put sodium chloride and see what happens. Yeah, we put sodium chloride and we are starting it. Let's see what happens. Some more sodium chloride. Okay, I just can you introduce yourself?
Zahid Manzoor.
From?
Dr. Mustafa.
So he is from Dr. Mustafa's group, who actually works in batteries and electrochemical cells. So they have made devices from acid and base solutions, and then they produced it's called fuel exhaling fuel cell. So they produce fuel cells that exhales or give rise to another fuel, right, given that initial solution of acid and bases. So now like sodium chloride is making the fan to work essentially. So we are harnessing the power that is there in a chemical into a mechanical one. So it's not a simple thing, and only thing is that how to harness that is very important, as I told you, right. Although we use sodium chloride for many processes in our body, but it is not, unless we have a proper electrode setup, we are not going to get the conversion of that into a mechanical work. But we can do, from glucose we could not get that, but from glucose we get in our body the ATP. So it's all about what machines and engines. So we can call this particular one now a machine. This machine is using, or this engine is using, the power of chemical energy to convert to mechanical energy, like all other machines, all other engines. So now this depends on what is the efficiency of the engine, how much conversion of initial input to output we are getting, and that will give us efficiency. So when you will talk about efficiency later on, you will see, we will talk about work that we get versus heat that we put input. Output by input is the efficiency. So how much food we eat to do how much amount of work, that is efficiency. If if you give me a lot of food, if I am not like efficient enough, I will not be able to do any work. Whereas a very thin guy taking a little bit of a food, he will run much longer. So it depends all on efficiency of, we are also engine, a much sophisticated engine where a lot of processes are happening. So thermodynamics will give you a limit to that efficiency. It will tell you that efficiency cannot be one. One cannot get the input output equivalent of input. We have to leave out something, and that leaving out for every tiny bit of processes, whether it is the process in our body, whether the process here, or all that thing we have shown, every tiny bit of processes, those leaving out, something that is leaving out, that is always there, and that is getting accumulated. And that we will learn that is nothing but entropy, which is getting accumulated, which does not have any end. It may have a beginning, but does not have an end. That's why it's called non-conserved quantity. All of us know that energy of the universe is conserved, right? It's not changing, it's same. However, entropy is non-conserved. It is always increasing. So that we'll later on discuss more about that.